Okay, so let's start with some basic probability. This is going to be fairly simple and straightforward, but let me just give a basic idea of the probability of an event occurring. And we write that, typically we write the probability of an event occurring I'm going to call it an event, and I'll call it event A occurring is written like this. It's written as the probability with A in there, okay? So this notation, P with parentheses A, means the probability of event A occurring. It doesn't mean P times A. It doesn't mean a P is a function of A. This is the notation in probability that means the P stands for the probability and A is the name of the event. And so if you want the probability, so we have two other things. You might have the probability of events A and B occurring. Oops, I got an extra. Is written probability of A and B. And you also could have the probability of A or B, which one event or the other occurring, or both. So this is the three different kind of notations we have: probability of A, probability of A and B, probability of A or B. And we have one more thing, and that's the probability of A occurring given that event B has already occurred. Oops, I got an extra C in there. And that's written probability of A with a vertical line B. Probability of A, we usually read this as probability of A given B, okay? So that's A given B. We use the word given there. So this means what's the likelihood that A will happen if we already know B happened? So in other words, you might ask a question, what's the probability that you're going to get an A on an upcoming quiz? Well, that will vary. You could just make a guess at that. And the other thing is, what you could ask another question, what's the probability of A, you getting an A on an upcoming quiz, given that you study with the person with the highest grade in the class for 3 hours the day before the quiz? So if you had that, right? If you were given that you got to study with the smartest person in the class the day before the quiz for several hours, don't you think your probability for A would be different? Does that make sense? Okay. So now let's go ahead and I'll clear all this. This is kind of the notation we have. And now finally, the idea of the probability of event occurring is equal to, it's a fraction, it's the possible ways event A can occur out of the total possible outcomes. And we always assume these are all equally likely possible outcomes. Assuming they're all equally likely to occur, how many different ways event A can occur out of the total possible outcomes in all? So it says here in this, look at this particular question, given a test to a group of students, the grades and gender are summarized below. So it says if one student was chosen at random. So when it says at random, that means any one of the students who took this test could have been picked. Like they took all their names and put their names in a hat and just randomly selected one of the names. That means they're equally likely to be chosen. Okay, so this is the case with pretty much everything we're going to be doing here. We're talking about random events. So if find the probability that the student got a B. So how many, if you had all these students' names or their grades, let's say, on pieces of paper, how many pieces of paper would you have total? How many things could you select from? How many people took the test then? Probability of A is equal to total test takers in this case. And this is number of B grades. So from the table, how many people got B's? Looks like 21 got B's. Some of them were male and some were female, but there were 21 people, and we're saying random, right? We're not, it doesn't matter if they're boys or girls. This is just anybody that the student got a B. So any of the people got a B. And the total number is 86. That's how many people took the test, right? You can see here, the total A's were 32 and 21 and 33. If you add those up, 32 and 21 is 53. 53 and 33 is 86. Also, the males, there were 42 males and 44 females. That's 86. So we know there's 86 total. So this is our answer, 21 out of 86. Now, you may be able to reduce that. In this case, the only things that divide 21 are 3 and 7. And 3 won't go into 86, and neither will 7. 7 times 4, 12 is 84. So this can't be reduced. So that's our answer, would be 21 out of 86. Now, if you put that on your calculator, if you put 21 out of 86 on your calculator, then you're going to get 0.244, 1 something. So now if you notice, if I'll click the answer, they don't give it in fraction form, they give you that decimal. Now, people have already worked on this assignment, and I found that if they went out even just 2 places here, it's likely that the answer would be marked incorrect. So I want you to see that if I change this and I put in, if I put in 21 divided by 86 as a fraction, you're guaranteed it's going to be correct. Okay, and so it checks it right. But if you go here and you say, okay, what do we say? 0.244. If I put in 0.24 and I check that answer, it marks it wrong. I mean, it's 0.24. You saw the key, 0.244. So they want more precision than that. Does that make sense? So let's see, would it take it if it was 0.244? Submit, and they did. If you went out 3 places, I would generally say if you go out 4 places, you'll be safe. There's just no reason to put a decimal in, though, because you can just write 21 out of 86 and you'll get full credit. You don't have to do anything. You don't even have to use your calculator for that problem. Okay, so let's, I'm going to clear all this and give a new version of the problem. And now take a minute and do that yourself, okay? I'll pause the recording. So yeah, the probability here is the probability that the student was a female would be the number of people who are female, which is 33, right? That's the 33, and the total would be 83. So it's 33 out of 83. So we can just enter that answer into our Place here 33, divide 83. Hit and submit. Oops, it didn't answer it, did it? Wonder why. 33 divide. Ooh. Oh, I know, my number lock is off. 33 divide 83. And that's okay. So let's go to the next problem. That's just kind of a basic idea of getting the fundamentals of probability down. Now the problems will get a little more interesting. Okay, so now we've got one with rolling die. Now, in general, when you roll a die, we're going to assume that those die have 6 faces, right? And that they're all equally likely. Now, die are not perfectly made, so they're not perfectly likely to land on every side, but it's pretty close. So we'll use that. This is the best way we can estimate is that we assume that they're equally likely. So what's the probability that the number showing is a 2? Well, on a 6-sided die, on a 6-face die, the numbers are it's numbered 1 through 6, and only one of them is a 2. So the probability you get a 2 on a die, there's only one number that's a 2, and there's 6 possible outcomes, right? There's only 1, 2, and there's 6 possible outcomes. So that should be 1/6, which we'll get now as a fraction that's just right 1/6. And now it says the probability that the number showing is an even number. Well, even numbers are 2, 4, and 6. So there's 3 even numbers. I'll just write probability of even. There's 3 even out of 6. Well, that's 1/2. We'll reduce that, the fraction. And lastly, I'm going to pause the video here and ask you to go ahead and you tell me the probability that the number showing is greater. So what's the probability that the number showing is greater than 1? Well, the probability, I'd write it this way. The probability, and I'll write it here, that I'm going to write x is greater than 1. Okay, x is going to be my outcome on the die. That the number is greater than 1 is equal to 5 out of 6 because there's 5 numbers greater than 1. Okay, so that should be 5 out of 6. And 1/6 is a decimal. If you divide 6 into 10, it goes 1 time with 4 left over. And so that will be 0.1, and that'll go in 6 times into 40, which is 36, and there'll be 4 left over. So that 6 is actually going to keep going on and on and on. So again, you probably want to put well, I wouldn't even put a decimal in there. Just put the fraction 1/6 in for your answer. But if you have to put a decimal in, if you end up doing that, you'd probably want to go out several places, like out that far, so you could get credit. So 1/2 is 0.5 is quicker for 1/2 probably. Now for 5/6, why not just put in 5 divided by 6? Now all of those, you can do decimals or a fraction that should give you, those probably all be correct, yeah. So this, I went out far enough. I think if I probably put if you round it off here at 1/7, it'll probably mark it wrong because you got to get a little, yeah, see, that's not accurate enough for it or precise enough for it. Okay. So let's go to the next problem. Okay. Now there's something called a complement. There's 2 ways to find how a person, looking at probabilities of somebody not getting something. So there's 2 different approaches on this type of problem. And so I'll write here the probability of not getting an A and that's sometimes called probability, if we write it like this, A complement with a little mark up there. That's another notation we have for that. Anyway, the probability of not getting an A, there's one way you could do that is you could take 100% minus the probability of actually getting an A, or that should be equal to the probability of all other possibilities other than A. Those are going to be the same thing. So let's do the other than A first. That means they could have gotten a B or a C, which that means there's 53 ways out of 76 that they didn't get, that they got something other than an A. Or you could take 1 minus, the probability of getting an A is 23 out of 76. Right, here's your A's total. Now 1 minus 23 out of 76 is, now you'd have to change this 1 to 76. And if you subtract 2376 from 76 minus 23 is 53 out of 76. So you get the same thing. Okay. So real quickly, let me just give you a new version of this and ask you to do that just for a few seconds. It shouldn't take but a moment. So again, two ways of doing this. You could take the probability of not getting an A, I'll write A complement like this, and that is 1 minus 24 over 71 because there's 24 A's, or you could have 14 plus 33, that is 47 out of 71. And again, if you take 1 and change it to 71 71st and subtract 24 71st, sure enough, 71 minus 24 is 47. So either way, you can do that. Sometimes this is a lot easier because notice here, you only have 14 and 33 as the two other possibilities, but there might be a long list of other possibilities. So it's a lot quicker to just subtract 1 minus the 24 over 71. If there were A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, and you wanted to not A, why not just do 1 minus the probability of getting an A? It'd be quicker. Okay. So next. So this is now a new type of probability that we haven't talked about, and that is when a dice is rolled twice. It says, what's the probability of showing a 1 on the first roll and an even number on the second roll? So this is probability of event A followed by event B. So that would be the probability of A times the probability of event B. So, and those could be actually, you could have the same event. In this case, it's the probability of getting a 1 on the first roll and then something different on the second. But even if it was event A occurring over and over and over again, you could do you use the same principle that you multiply those two probabilities. Event A followed by event B. And this is, by the way, this assumes they're independent. They're called independent events. That is, the result of the second event doesn't depend on the result of the first event. So, so let's take a look at this one. So a die is rolled twice. So the first event is event A. What's the probability that it shows a 1 on the first roll? Well, that's to get a 1, there's only 1 1 on the first roll and there's 6 faces. And then on the to get an even on the second roll, that was 3 evens, a 2, 4, or a 6 on the second roll. So you get 1 6 times 3 6. Now you can go ahead and reduce this 1 3 6 to 1 over 2 before you multiply, and that'll give you, remember, you multiply numerators, that's 1, and you multiply denominators, that's 12. So that should just be 1/12. Okay, that would be your result here, is 1 out of 12. Okay, so I'm going to go ahead and clear that, and I'm going to pick a new version and have you do that version. That's, oh, this is pretty much the same. So it's a 5 on the first roll, and the probability of that is still 1 out of 6, and an even on the second is still that. So let's see if they have a more mix. No, this is still, it's always just some number and an even on the second. So these are all going to be the same. Okay, let's go to the next problem that I think will give us, this will give us something more interesting. So this is a similar type of problem, but now we have bags of cookies. It contains 9 chocolate chips cookies, 5 peanut butter, and 9 sugar cookies, and 5 oatmeal cookies. Wow, I'm trying to reduce my cookie consumption. This is tempting me. But anyway, what is the probability that Alan reaches in the bag and randomly selects a sugar cookie from the bag, eats it, then reaches back in the bag and randomly selects a chocolate chip cookie? Now, these are not independent events, because whatever happens after the first event, then the second event, it's going to change what happened to the second event, because the bag has a different number of cookies in it. And I'll show you what I mean by that in this. So first, what's the probability that Alan reaches in the bag and randomly selects a sugar cookie from the bag, and then he eats it? That's the big deal. He eats it, and then he reaches back in the bag and randomly selects a chocolate chip cookie. So we've got the probability that, first I'm going to put S, I think that's the only S one, an S, and we're going to multiply that by the probability that he gets on. The second one is a chocolate chip, so I'll call that a C, chocolate chip cookie. So what's the probability that he gets a sugar cookie when he first picks it? Well, there's 9 sugar cookies. So there's, if these are randomly selected, right? He randomly selects a sugar cookie. He's got 9 chances to get a sugar cookie, right? But what's the total number here? Well, the total number of cookies is 9 plus 5 plus 9 plus 5, which is 28. So it's 9 out of 28 to get a sugar cookie. And now, what has happened to the bag? There's still 9 chocolate chip cookies. There's still 5 peanut butter cookies. But now there's, for the second event, this has become 8. There's now only 8 sugar cookies because he ate one of them. Anyway, and there's 5 oatmeal cookies. So the probability that he gets a chocolate chip cookie on the second selection, there's still 9 chocolate chip cookies in the bag on the second pick. So that's still a 9, but there are no longer 28 cookies because he ate one. So this is now 27. Does that make sense? So let's go ahead, and I'm going to do a little reducing here, because the 9 and 27 reduce to 1 and 3. And actually the 3 and the 9 will reduce to 1 and 3, that 1 and 3 that way. And so that's going to give us 3 out of 28 for that. And that's what I'd enter in there, is 3 out of 28 for your final answer. Okay. So I'm going to go ahead and clear that. And notice that if he would have not eaten the cookie and put it back in, then it would have been 9 out of 28 times 9 out of 28. But since he ate it and didn't return it, there were fewer cookies. So you always want to have to watch out for that. So those are somewhat, they're not completely independent. This probability changes. So I'm going to clear that, give you another version. Okay, we've got different number of cookies here, 12, 14, sure. So let's take, I'm going to pause this for a minute, pause your video, and try and do that problem. So here we see that it would be 6 out of 26 because there are 6 peanut butter cookies, and there's a total of 26 cookies. And then if you eat the 1 peanut butter cookie, there's only 25 cookies to follow. And so there's 8 chocolate chips out of 25. So we can reduce the 626 to 3/13 and get 24 over 325 if we multiply those. Or you could just multiply 6 times 8 to get 48 and 26 times 25 to get 650. And I think either one of those answers, I think they, even if you don't reduce it, I think this will be, I think they give you full credit even if you don't reduce. Let's just see. See, there you go. So you can just multiply straight across. Okay. Next problem. We got a couple left. So now it says, giving a test to a group of students, the grades and gender are summarized, gender are summarized below. If one student is chosen at random, it says find the probability that the student was male and got a C. So this has to be people who were male and also got a C. So we can see, I like to do this, if they were male, they would have to be in this row. And if they got a C, they'd have to be in this column. And so the overlap there, that is, there's 13 that were in both the row and column. This is 13 males that got C's, right? So that would just be 13 out of a total of 69, because it said they're chosen at random, and we assume that's out of the whole group. So it's 13 out of 69. Now, that is, and 13 times 5 is 65, so that's not reducible, so you can just write 13 out of 65 on that. Okay, let's go ahead and clear that. That would be our answer there, 13 out of 69. And as a decimal, 13 out of 69. I'm getting 0.1884 something. And I think I'd probably take that at least out to 1884 at the very least, or maybe 188406 or something like that. Okay, so let's clear that, and I'm going to give a new version. And now take a minute to pause the video and do this problem. Okay, so this one's pretty straightforward, very similar to the last problem. There's three of the students that were male and got a B, and out of 42. Okay, and so 3 out of 42 reduces to 1 out of 14. All right, let's take a look at the next problem. Should have an OR problem here. So this is an OR probability. Now we haven't talked about how to calculate OR probabilities. They're very different. So let's go ahead and read through this. Says the table summarizes results from a 975 pedestrian deaths that were caused by automobile accidents. So this is where someone was walking and somehow they were involved in the automobile accident. And somehow, sometimes alcohol is involved. And so notice there's a total of 975. And do you notice they don't have the column, they don't have this third column where these are added up or these are added up. Do you see that? In the other tables, these were always extended, in the previous tables. So we had that going on. See? So it might benefit us to look at that. You could add this is all the times the pedestrians were intoxicated, and that's 57 and 215. So that's what, 272 times where the pedestrians were intoxicated. And this is where the pedestrians were not intoxicated, 68 and 635. So that's 8 and 5 is 13. Carry the one that's 10. Carry the one that's 7. So very interesting. Pretty high percentage of the time that the pedestrians were intoxicated in those accidents. Not most of the time, but that's pretty significant. It's about a fourth of the time. And now where the drivers were intoxicated, 57 and 68, that's 125, right? And then 215 and 635, that's 850. And so we should be able to add these and make sure that comes up to 975. So I'm just verifying that. 125 and 850 is 975, and 272 and 703 is also 975. So that all checks out. I just want you to see that this is what our previous charts were looking like. And if you didn't have those numbers, you can just complete the chart if you want. So anyway, it says, if one of the pedestrians' deaths is randomly selected, that means any of these have an equal likelihood of getting picked, okay? And, oh, any of the pedestrian deaths, all these are where a pedestrian died. Find the probability that the pedestrian was intoxicated or the driver was not intoxicated. Okay, so that's, I'm gonna write that up here. This is the probability that the ped was intoxicated or, I'm going to put it in capitals, or the driver was not intoxicated. Okay, abbreviate that. Now, you want to pay pretty close attention to this. When you have or probability, the probability that you have, I'm going to call this event A, well, I'll call this PI, probability that the pedestrian's intoxicated, or the probability that the driver was not intoxicated. When you have an or probability, you take the probability that the pedestrian was intoxicated plus the probability that the driver was not intoxicated minus the probability of both PI and driver not intoxicated. Okay, so that is, we want to find out the probability that a pedestrian was intoxicated. This is a pretty easy calculation to make. We can look at the table and say, if you pick one of these events, what's the probability that the pedestrian was intoxicated? Well, here's the pedestrians. Here's the column for yes. So that's a total of 272 people. So there's 272 pedestrians who were intoxicated, right? Out of how many? 975. Now, how many of the drivers were not intoxicated? So now we go to the driver one and we look at the no row for drivers. These were all the accidents where a pedestrian died and the driver was not intoxicated, of which there were 850 of them. So that's 850 out of 975. Now, this is something we haven't talked about yet, but is a crucial element, an idea in probability. One is that the highest likelihood that anything could occur, the highest possible probability, is 100%. That is equals 1. You can never have more than 100% probability, okay? And the lowest possible probability is what, do you think? Hopefully you know nothing can be less than 0%. So all probabilities are between 0 and 1. And if you take a look at this, 272 over 975 plus 850 over 975, well, 272 and 850 is more than 1,000. If you add those together, you'll get over 1,000 something over 975, which is bigger than 1, which would make it more than 100%. You can never, ever get an answer that's more than 100% in probabilities. If you do, there's been an error made. So what you have to do is look at this and say, hey, this is called the overlap. The and is the overlap. In other words, look at the column for the pedestrians where we got that number, where we got 272 right here. What did it include? It included the 57 where the drivers were intoxicated, and included the 215 where the drivers were not intoxicated. And now let's go to the next one, the probability that the driver was not intoxicated. Where did that 850 come from? It came from the drivers who were not intoxicated row, the 215 where the pedestrian was intoxicated, and the 635 where the pedestrians were not intoxicated made up this 850. So how do we get 850? It's the 275 plus 635. And how do we get 272? It was 57 plus the 215. So this 215 got added in this column. It's part of the 272. And the 215 is also part of the 850. And that is where they were both, the pedestrian was intoxicated, yes, and the driver was not intoxicated, no. So that 215 got counted twice. Okay, so we'd have to then go and just add up those. Now this is addition, not multiplication. So we have the same denominator, 272 plus 850 minus 215. And I'm getting 907 there. 907 out of 975. And if I put that 907 out of 975, that's approximately 0.9302564. And we don't need to go out that far. I'm just going to put the 907 over 975 in here. Well, I'll look at what the decimals. So, oh, it says a percent. I'm sorry, I did. It does say to report the answer as a percent. So we would have needed to do that. And it says to 1 decimal place accuracy. So that would have had, you had to multiply this by 100%. I didn't read those instructions, did I? Times 100%. And so that's going to be 93.02564%. And yeah, you can round that off to just 93 then. Okay, so I'm going to go ahead and clear that and remind you of the formula. The probability of an event A or B occurring, when you have an or, you take the probability of A, add to it the probability of B, and then watch out, because if there's an overlap where A and B both occur, just put in parentheses here, this is called the overlap, where you have double counted, okay? So you'd have to subtract that overlap. So let's go ahead and get a new, oops, wrong. Okay, this is a new problem, right? Got new numbers here. This is where there's 980 pedestrian deaths that are caused by automobile accidents. And it says if one pedestrian, if one of the pedestrian deaths is randomly selected, find the probability that the pedestrian was not intoxicated or the driver was intoxicated. So this is asking for different things this time. So the pedestrian was not intoxicated. So make sure you pick the right column for that. And then that the driver was intoxicated. So make sure you get, this one's going to be the correct column, right? So make sure you get the right column for that one. And this one is going to be the drivers. This is in a row. So make sure you get the right row for that. And I'm going to go ahead and pause this, take a minute and pause this video and try and complete that problem. Okay, so hopefully you got that sorted out. The first thing you should have done was found out, if we use this method, is you find out the total pedestrians who were not intoxicated. So that would be in this second column Pedestrians intoxicated, no. You had 71 and 591 to give you 662. And then the driver was intoxicated, so you go to the yes column on that, and you get 59 plus 71, which is 130. So that's your probability that the driver was intoxicated. And now you have to subtract the overlap. And that is where the pedestrian was not intoxicated and the driver was intoxicated. And that is the 71. That is where there's an overlap. That was in both this row, the yes row for driver intoxicated, and the no row column for the pedestrian not intoxicated. So we add those up. Now, quickly, you don't have to use that formula when you've got a table like this. It's also possible just to go through and say, okay, we've got pedestrians not intoxicated and drivers are intoxicated. So the drivers, yes, we would take this row, the pedestrians no would be this column, and you could just go 59 plus 71 plus 591. Instead of getting this row total and that column total, then you could just do those three and you wouldn't have any overlap because you're not double counting the 71. You only count the 71 once. And that's still going to be over 980. So 650, 720. Well, I think that was 721 out of 980 that way too. And that's nice if you've got a nice table that you can get that information from. But you also need to be aware that sometimes the table isn't as easy. And so that formula of adding the probability of A plus probability of B minus the probability of the overlap is important to know how to do as well. Okay, we have one last problem. And this is the first of conditional probability. And Wednesday, the lesson will be mostly about conditional probability. It will be about expected value. And conditional probability gets quite a bit more complicated. And so this will be this is just a basic introduction of conditional probability. And this is where we have the probability of A given, and I showed you this notation, given B. So that means we always assume that B has occurred, okay, or B has been satisfied in some way. So, hi, Sydney, by the way. So it says if one student is chosen at random from those who took the test, find the probability that the student was female given they got an A. So this is a little misleading because it says from those who took the test, but it's telling you here that they had to have gotten an A already. So your total, the denominator here, and this little bar hopefully can help you understand that. The B group is what you have to be in. That is, they have to have gotten an A. So what I do is if they have to have gotten an A, we have to look down the A column because this is not saying we're finding the probability that the student was a female given they got an A. That means we aren't concerned with those people who got a B. We aren't concerned with the people who got a C. We aren't even concerned with the total because all we're concerned with is they're telling us that they already got an A. We know this is only from the A group. So now, basically all you do is you look down that A column. And so how many people are in the A column? How many people got an A to begin with that you're picking from? It would be 10. And how many people from that 10, how many of those were female? Well, that was 8. So that's just 8 out of 10, which would be 80%, or 4 out of 5 if you want to reduce the fraction. Okay, so let's clear that, and I'll give you another version of that. It should be different. That one's the same. Let's do that. Okay, let me see if I change it. Oh, it's always about the A, isn't it? Okay, let's do this one. Okay, find the probability that the student was male given they got a B. Okay, I'm going to pause the video here. Okay. So hope you've had a time minute. You paused your video and you set this up. So again, the base here is given. It is given that they got a B. So the first thing we're going to do is go to that B column. The B column right here. And that B column is the basis. That's why I put it's male given they got a B. B tells you what your denominator is going to be. There's a total of 22 people who got B's in that on that test. And the probability that they were male, if they were in that group of 22, of all the 22 B's, there were 3 of them that were male. So that's 3 out of 22. So it would not be the 22 out of 61. 3 out of 22. Okay, let's clear that. I'm going to give another, just a new version of that. Actually, I'm not going to give a new version of that. I'm going to give you my own problem here. I'm going to make one up here. So now, what is the probability that a person got a C given they were female? Okay, so that's, again, I'll pause the video for a second and have you try and do that. Should,
Wait,
okay.
there's two. Oh, I didn't notice that there were 2 total columns.
Yeah, there's
Okay.
a total for grades and there's a total for males and females, your gender. So yeah, so since it's a female is the given, then you have to go to the female row rather than the column. So you go to the row, there's 32 in all females. There's 32 females. So that gives you your total of 32 down here.
Okay, I understand now.
Okay.
All right.
And then the number of C's is 18. And of course, that can be reduced, you know, that'll be 9 out of 16 if you reduce it, or you can write it as a decimal. Okay, so that is it. We have, if you have any questions, I'm going to go ahead and stop the recording right now.